time, the changes in the British climate have been startling. I can remember huge snowdrifts in the 1960s and the sea freezing when I lived in Southend-on-Sea in Essex. As a keen skier in the 70s and 80s, I can recall skiing in the Cairngorms regularly from November right through to the end of March. Nowadays, skiing in the Cairngorms is a rarity at any time in winter. Small climatic changes noticeable over one lifetime are evidence of something very significant going on in the atmosphere. The changes in the British Isles have been small, yet noticeable. In other parts of the world, faster rising sea levels and advancing deserts pose a threat to homes and livelihoods, which are very serious. There's a wide variety of evidence which tells us that the activity in the Earth-atmosphere system has changed over the centuries. Many of these changes have left their mark on the landscape, and there is a wide variety of techniques which can be used to investigate how past climatic change has happened. Pollen analysis, dendrochronology, and isotope analysis, which includes within it ocean floor analysis and ice core analysis, are the most widely used. Pollen analysis is concerned with examining the pollen found in sediments, particularly peat bogs, which preserves the pollen grains for a long time. And this analysis can identify past vegetation and hence indicate past climates. This form of analysis is particularly useful in detecting climatic changes since the last glaciation, which ended round about 10,300 years ago. Dendrochronology is a study of growth rings across tree trunks. Thick rings indicate a favourable climate, and thin rings indicate poor conditions. Each ring represents 1 year's growth. And to attain an accurate climatic reconstruction using this method, cores are taken from a number of different trees and their rings cross-matched. In California, some bristlecone pines last as long as 4,000 years, and they have been used for this sort of analysis. In the British Isles, we've used oak timbers, which has constructed a past climate from around about 400 AD to the present. Isotope analysis has concentrated on the examination of oxygen isotopes. The two main isotopes of oxygen are O16 and O18, and these occur in water and in ice, and in water vapour also. They move through the hydrological cycle differently, largely because of the weight difference. O16 being slightly lighter, it passes into the water vapour stage more readily. This results in the remaining water being enriched in O18. Condensation reverses this process and restores the balance. However, during cold spells, more precipitation is locked up in ice sheets and the return flow is diminished. The colder the climate, the greater the O18 concentration in seawater. Isotope ratios can therefore be used to indicate temperature. An ice core analysis measures oxygen isotopes in the polar ice sheets where snow has accumulated over thousands of years. The ocean floor analysis also looks at oxygen isotopes, but it's the remnants of tiny organisms which are buried in their sediments which contain the oxygen isotopes, and the relative proportions of these indicate the temperature of the water at any time. The idea of built-in climate change in the Earth-atmosphere system was first proposed by a Scot, James Croll, in 1860, and a Yugoslavian astrophysicist, Milankovic, reintroduced the theory in the 1930s. The fact that the shape of the Earth's orbit around the Sun, the angle of tilt of the Earth, and the time of the year when the Earth is closest to the Sun change through time in well-defined cycles, led Milankovitch to argue when the lowest phases of insolation in all cycles combine, glaciations would occur. His predictions for past ice ages have received some support from ocean floor sediment analysis since his theory was postulated in the 1930s. But despite the accuracy of his predictions, for some, Milankovich's theory does not offer a full enough explanation. There are other earthbound theories of climate change which have been suggested. One of these proposes that periods of volcanic activity trigger off cold periods because volcanic dust and sulfur dioxide blown into the atmosphere reduce insolation by scattering solar insolation. Explosive volcanic eruptions can be a major cause of natural temperature reductions on a short-term scale of, say, less than 10 years. Another theory of climatic change is based on possible shifts in Rossby waves, which could cause a redistribution of temperature along lines of latitude, causing a fall in average temperature. And this, under certain conditions, could increase snowfall to the point where a glaciation might proceed. We know that El Nino, the southern oscillation, is a large-scale ocean atmosphere system which is associated with strong fluctuations in ocean currents and surface temperatures. It has long been known as one of the best understood regional climatic influences. It significantly influences regional climate, and it can exert a small influence globally. It causes periodic atmospheric and environmental changes in the equatorial zone of the Pacific Basin. The ENSO is a major example of how ocean currents and atmospheric conditions are connected. During a warm ocean event, sea level pressure drops in the eastern Pacific and rises in the west. This weakens the easterly trade winds as the Walker cell moves eastward. This can result in drought over Australia and parts of Southeast Asia and South America. Heavy rains might occur in Peru and Ecuador, which are adjacent to the warmer ocean water. In the early 19th century, Frenchman Joseph Fourier, in his study of heat, showed that the atmosphere kept the Earth warmer than it would be if exposed directly to outer space. John Tyndall, an Irish physicist around 1860, had found that this warming lay in the properties of some atmospheric gases, including carbon dioxide. These gases are transparent to visible light, but absorb infrared radiation, meaning they let sunlight in but impede heat from getting out. In the early 20th century, Svante Arrhenius, a Swedish chemist, was suggesting that low carbon dioxide levels might have caused the ice ages, and the industrial use of coal might warm the planet. There are numerous examples of ancient civilizations collapsing because we weren't able to adapt to changing climatic conditions. For example, the Mayans of Central America, the Akkadian Empire of ancient Mesopotamia, and the Khmer of Southeast Asia. Archaeologists rarely find any evidence that these societies made any significant attempts to change in the face of climatic challenge. This inflexibility is the ultimate reason for the collapse. In the 21st century, the choice is clear: adapt or face an uncertain future. The largest recorded volcanic eruption at Tambora in the Pacific in 1815 resulted in poor weather throughout Europe in 1816. It became known as the year without summer and inspired Byron's poem Darkness and Mary Shelley's story Frankenstein. The top graph shows the frequency of ice ages and the warm interglacial periods. The second graph shows the warming since the last ice age, and the third graph shows the Little Ice Age, which was a period of much colder conditions, roughly between AD 1300 and 1850. The coldest period of this global cooling was between 1645 and 1715, when average winter temperatures in Europe and North America were as much as 2 degrees lower than at present. These conditions led to widespread crop failure, famine, and population decline. Now, although there might have been other factors influencing this cold period, it seems likely that reduced solar activity was a major contributing factor to this cooling. Climate change became more of a concern from the 1980s, with extreme weather conditions becoming commonplace and global warming accelerating. And you can see from 1980 in this graph, global temperatures have accelerated fairly rapidly. Evidence for linking carbon dioxide and global temperatures was established in 1982 when research into past carbon dioxide levels was matched against global temperatures. This research showed that when carbon dioxide levels rise, then there's a rise in temperature which follows, and when carbon dioxide levels fall, a temperature fall follows. The graph below shows how temperature has followed carbon dioxide concentration over the last 600,000 years. In spite of uncertainties, climate models have done a pretty good job of predicting what has happened so far. Although the half a degree centigrade rise in global temperatures between 1960 and 1990 is consistent with the greenhouse effect and the 6 warmest years on record that have occurred really since the 1980s. As of 2019, the 18 warmest years on record had occurred since 2001. Now, the enhanced greenhouse effect is here. In 1990, Dr. James Hansen of NASA, along with colleagues, used a computer simulation of global circulation to produce year-by-year predictions of global temperature. And Hansen produced predictions for 3 scenarios, shown on the graph. Hansen's predictions have proved to be very accurate, with a track of global warming very closely following to scenario B, with around a 1 degree centigrade warming between 1960 and 2017. The UK government were so convinced of the argument that climate change was happening, it produced a document outlining the evidence and possible options for action as far back as 1989. This graph shows the steady reduction in the extent of Arctic sea ice since records started in 1978. It's very likely that warming of air temperature will progress more rapidly over land areas than over oceans, and that warming over the Arctic in winter will be greater than the global average. This means there will be a further shrinking and thinning of Arctic sea ice, decrease the northern springtime snow cover, and melting of near-surface permafrost. This graph shows how the NASA satellite data has determined the rise in sea level since 1993. Current sea levels are rising at a rate of 3.3 millimetres per year. Now, however serious the effects might be in Britain, they would be much worse in countries such as the Netherlands, Bangladesh and Egypt, which are lower lying. But major global cities such as London, New York and Shanghai are also very vulnerable. Already some parts of the world are suffering from rising sea levels. In 1994, two American scientists, Sherwood Rowland and Mario Molina, warned that chlorofluorocarbons, CFCs, could destroy ozone in the atmosphere. They were convinced that CFCs, which are found in, or were found really in aerosols and refrigerants, could rise in the atmosphere until sunlight breaks them down to release chlorine, which in turn would destroy ozone. CFCs are synthetic gases which are inert, relatively non-toxic, non-flammable, and without smell or colour. However, CFCs can last in the atmosphere for well over 100 years, and one molecule of CFC can destroy thousands of ozone molecules. What was worrying that ozone was being destroyed faster than it was being created, and concern about this threat led to the Vienna Convention in 1985, which covered matters such as research, but the Montreal Protocol 2 years later required cuts of CFCs by 50%, and that was signed by 30 countries. And since then there has been a toughening up of action against chlorofluorocarbons and also HCFCs, which are also of concern. Solutions to global warming. There are any number of possible solutions which might have an impact, and I've listed just some of them here. Obviously, using alternative refrigerants to chlorofluorocarbons and HCFCs would be an important step. It took 2 years from the discovery of ozone depletion over the Antarctic for the global community to adopt a legally mandated course of action. Only now, the ozone layer is beginning to heal, 3 decades later. We could also reduce food waste. An estimated third of the food produced does not make its way from farm or factory to the table, while at the same time 800 million people worldwide struggle to survive. The food we waste contributes to 4.4 gigatons of CO2 equivalent into the atmosphere, roughly 8% of the total greenhouse gas emissions. A plant-rich diet could be encouraged. The diet of developed countries comes with a fairly steep environmental price tag. Conservative estimates suggest that livestock account for nearly 15% of global greenhouse gases emitted each year. Climate, health and economic benefits of a worldwide transition to a more plant-based diet between now and 2050 could cut emissions significantly. We need to preserve and replant tropical forests which take in carbon dioxide and breathe out oxygen. It's the natural way to affect carbon capture. In recent decades, tropical forests have suffered extensive clearing, fragmentation, degradation, depletion of flora and fauna. Once blanketing 12% of the world's land masses, they now cover only 5%. Tropical forest loss alone is estimated to be responsible for somewhere between 16 and 19% of greenhouse gas emissions caused by human activity. There are a range of other carbon capture initiatives. Broadly, they fall into three categories: increasing biological uptake, such as forestry, wetlands, and agriculture; increasing inorganic reactions with rocks, carbon storage underground or on the surface; or indeed engineering direct capture from the atmosphere. Alternatives to fossil fuels for heat and power are also one area, but we should also consider stopping subsidizing the fossil fuel lobby. Globally, for every $1 spent to support renewable energy, another 6 are spent on fossil fuel subsidies. These subsidies are intended to protect companies and consumers from fluctuating fuel prices. But what they actually do is keep the dirty energy companies very profitable. In agriculture, we could encourage silvopastoral systems. These sequester carbon in both the biomass above the ground and the soil below. And pastures that are crisscrossed with trees, we have estimated that they sequester somewhere between 5 and 10 times as much carbon as a treeless landscape. Moreover, because the livestock yield on a silvopasture plot is higher, it may curtail the need for additional pasture space, and thus help avoid deforestation and subsequent carbon emissions. And lastly, we could consider reducing emissions from transport. There has been a slow switch from gas-guzzling cars and buses to electric power, and this trend seems likely to continue. The entire transport sector, which includes air, sea, and land transport, accounts for around 15% of all greenhouse gas emissions. Now, what would happen to the climate if we were to stop emissions immediately? It's unlikely, but the large oceans build inertia into the world climate system, and the long lifetime of many greenhouse gases, primarily carbon dioxide, means that much of the warming impact will persist for centuries after greenhouse gas emissions have stopped. For a recent emission, about half is removed within a few decades, but the remaining fraction stays in the atmosphere for much longer. It's estimated somewhere between 15 and 40% of the CO2 produced would still be in the atmosphere after 1,000 years. Man-made greenhouse gases will persist long after emissions have ceased. Concentrations of greenhouse gases would not return to the pre-industrial levels if emissions were halted. Methane concentration could return to close to natural values in about 50 years. Nitrous oxide would take several centuries. And for CO2, it would essentially never come back to pre-industrial levels. If concentrations of greenhouse gases were constant at present-day levels, the Earth's surface would continue to warm by about 0.6 of a degree centigrade over the 21st century, relative to the temperature of 2000. This is a climate commitment to current concentrations, even if greenhouse gases were halted. The impact due to these long-lived greenhouse gas concentrations would only slowly decrease in the future, at a rate determined by the lifetime of the gases. Global temperatures would not respond quickly to the greenhouse gas concentration changes. Eliminating all emissions to zero would therefore, after a short warming, lead to a near stabilization of the climate for multiple centuries. This is termed the commitment from past emissions. The inertia of the climate system would delay the temperature response. The long-term global temperature is largely controlled by the total CO2 emissions that have accumulated over time, irrespective of the time when they were emitted. If you're interested in finding out more about how our atmosphere works and more detail on climate change, check out my book, The Atmosphere and Climate Change, available for Kindle and in paperback from Amazon. My website also contains downloadable courses, including one on the atmosphere and climate change, which can be used in conjunction with the book or with other textbooks for senior school pupils.